now we are done with the encoder and we start looking at the decoder, right? So the decoder, of course, operates in sequence. Right? It operates sequentially because it generates one output, then that output feeds in as the input while generating the next output, and so on, right? So now what does the decoder look like, right? So the decoder, of course, takes input from the encoder also. So as I said, the output of the encoder is E1 up to ET, right? This layer. So this is, of course, fed as the decoder, right? Because the decoder needs the context of what the input was. What is it translating, right? So that contextual representation you have captured at the last layer, and that you feed to the decoder. So the decoder is going to get inputs from the encoder. It's also going to have its self inputs, right? Which is the inputs of the words that have been decoded so far, right? So it will have these two types of inputs, and let's see how it deals with these two types of inputs, right? So yeah, so what would be the output dimension, right? So let's first look at that too. So we know what the inputs are. Now we look at the output. So the output, and what do I need to generate at the output? Again, this is not new to you. You have already seen this in the context of RNNs. So each output here would tell you a probability distribution over the vocabulary, right? And you will take the arg max from there, right? So you would want that if there are 37,000 words, so that's what the number 37,000 is, then you will get the probability of each of these 37,000 tokens, and hopefully at the first position, this should have been go actually, right? So let's assume there's a go input here, and this is the first position. So you hope that at the first position, Nan has the maximum probability because that's the correct translation. Then at the second position, Transformer has the right probability because that's the correct translation, and so on. Right? You continue like that till you produce stop at the last position. Right? So your output is a probability distribution over the entire vocabulary. Hence, the output dimension is 1 cross 37,000, where 37,000 is the size of the vocabulary. So in general, I should just say it is of size V. Right? That's what I should have said. So now we understand what the inputs and outputs for the decoder are. So now let's just zoom into what the decoder actually contains, right? So just like the encoder, the decoder would also be a multi-layered network. So it would have, say, typically 6 to 12, 8, depending on the kind of training data you have, the amount of training data you have, the kind of problem that you're dealing with, you would have any number of layers, but the most basic ones have 6, 8 or 12 layers, right? So there are 12 layers of processing happening, and just as in the case of encoder, each of these layers has an identical structure, right? So whatever is happening within a layer is the same. It's just that the output of one layer acts as the input to the next layer, right? So that's the same as what we had in the encoder. But now what we need to look at is what is inside each of these layers, right? That's what we need to understand. So let's zoom into one such layer. So you will have the inputs. So these are the small h number of time steps which have been decoded so far, right? All the inputs have not been available because whatever has been decoded, that comes in as input. So whatever, how many steps have been decoded so far, only that many inputs would exist, right? Then you have something known as the masked multi-head self-attention, right? So there's this masked word which has been introduced here, okay? Then again at the output of one layer, you have the feed-forward network. So this, as I said, is the same, exactly the same as what we saw earlier, right? So again, the same thing is going to happen here. You would have these inputs H1 up to H capital T, right? Which would give you some intermediate outputs S1, S2 up to ST. Then maybe there's some space here, maybe something else would come. So maybe you'll get some other outputs, let me call them M1, M2 up to MT. And then finally, all of that will pass to the feed-forward network, and you will get the outputs Z1, Z2 up to ZT, right? And then this process will repeat across layers. And in the final layer, you will have the output projection to a softmax layer, right? You'll have a softmax layer which will predict a probability distribution over the vocabulary, which will hopefully peak at the right word, right? So this is what is happening here. So I need to explain what is this masked and what is happening in between here, right? So these are the two things that I want to explain, which are different than what happens in the encoder, right? Yeah, so this is what happens. So you have the encoder inputs coming, right? Those were the E's, right? So in addition, it's of its own inputs, which is the self part. It also gets inputs from the encoder. and hence you have a multi-headed cross attention, right? Cross because this is between the encoder and the decoder, hence you have the cross attention layer. Then the output of the cross attention layer goes to the feed-forward network, right? So again, I will repeat this as many times as required. At every stage, you have, I should not call it T, but say suppose capital T1, right? Because the number of words in the input may be different for the number of words in the output, right? In source language, you might have 6 words. In target language, you might have 8 words to say the same thing. So you'll have capital T1 inputs here. Again, at this point, capital T1 intermediate representations would be computed. Again, here capital T1 intermediate representations would be computed. And then again here capital T1 output representations would be computed. This is one layer. Then these T1 outputs would feed to the next layer, and again the same processing would happen, right? And all of this entire block is happening in parallel, right? All these computations are happening in parallel. Of course, like what I mean by that is all these T1 outputs are getting computed in parallel, then all these T1 outputs are getting computed in parallel, then all these T1 outputs are getting computed in parallel, right? So now what is this masked and what is the multi-head cross attention? These are the two things that we need to understand. Okay, so now we'll try to understand what the masked self-attention and the multi-headed cross-attention looks like, right? So we have these inputs. So we'll assume, right, in any case. Now, one question, of course, is that in the case of the encoder, you know that the sequence is of length t because that is the input given to you, right? But in the case of the decoder, how do you know what the sequence length is, right? Because you don't know what the output is. You're trying to generate the output. So the length of the output is unknown to you because unless you generate the stop signal or the stop word, you don't really know what the length of the output is, right? So you'll assume some max sequence length, right? And let me call that max sequence length as T1, right? So that's for the max sequence length that you will assume. But now when you start producing the first word, right? At that time you have T1 inputs, right? Of which only one is valid because that's the go word, and you know that okay, go is the start signal that I get, but all of these are junk, right? You don't know what these are, right? And now what are you going to do for each of these? You are going to compute the Q, K and V vectors, right? So these are the capital T1 inputs given to you, right? And you're going to compute the Q1, K1, V1, right? The Q matrix, the query matrix, the key matrix and the value matrix, right? But while doing that, you are aware that whatever value you're getting for these guys, right? That does not make sense. Whatever key you are getting for these guys does not make sense. Whatever query you are getting for these guys, this does not make sense because these are some junk inputs. You don't even know, right? This might just be a special symbol saying empty, right? You don't know what it is right now, right? So when you're computing a refined representation for Go, right? Then let me call that as Z1, or rather, sorry, let me not make those mistakes again, right? So I'm going to call this as S1, right? When I'm going to compute a refined representation for S1, I don't, so S1, if you remember, is going to be summation alpha over all the Vj's, where J's go from 1 to T1, right? But from V2 to Vt, I don't trust my inputs because there are some junk inputs, right? I don't even know what symbols should come there. So it does not make sense for me to compute a refined representation using V2 to Vt, right? So what I will do, and that's why this is called masked self-attention, is I'll make these alphas 0, right? So whatever alpha is greater than the current decoded word, I will make those 0, right? So alpha 2 to alpha capital T will become 0. So these V's will not participate in the computation. So S1 would only depend on the representation of Go, right? And in the first case, it makes sense, right? But now as you go deeper, at the first case, you might think this is just trivial, right? But now as you go deeper, let's understand what will happen, right? So now suppose you have decoded this much, right? You have Go, NaN and transformer, right? So you have these three inputs available to you. Now you are computing a refined representation Z1, Z2, Z3 all the way up to ZT1, right? Now what will you do when you're computing Z1? Your formula was alpha into Vj, j is equal to 1 to capital T1. But now since you have decoded up till time step 3, you will let alpha 1, alpha 2, alpha 3 be whatever they were, right? And then you will set the remaining ones to 0, right? That's what you will do. That's what masking does. So the masking means that zeroing out the attention weights which do not matter, right? I'm just doing a slight abuse of explanation here, in the sense that the alphas need to sum up to 1, right? So while you mask out the 0, you'll also do something so that these 3 now scale them up so that they sum up to 1, right? But that is internal detail. What you need to understand conceptually is that when you're computing a refined representation of a Z1, you will set all the other alphas to 0, right? Similarly, so this I should call as alpha 1j. So this is alpha 1 1, alpha 1 2, alpha 1 3. Now similarly, when you're computing the refined representation for Z2, your equation would be alpha 2j into Vj, and again alpha 21, alpha 22, alpha 23 is what you care about, and all the other alphas you will set to 0, right? So that's all that masking does, right? Now your question would be that what happens to Z4, right? So I'm going to compute Z4, right? Z4 would also have a formula. So in that formula, what do I do, right? So you will again have only these alphas ready in that formula. All the other alphas would not be of use, but actually it doesn't matter, right? Because again, when you are doing, so the key thing to realize here is that these did not participate in the computation, right? These gave you the corresponding Q, K and V, but when it was time to use those V's, you just zeroed out the weights, right? So irrespective of what your input was, this did not participate in the computation. Similarly, whatever you compute here will not participate in the rest of the computation, because the corresponding alphas would always be zeroed out. You'll always use this masking, right? Here also you will have a masking. So only that part of the input which is currently being decoded is going to participate in the computations. The rest of the input will get masked out because you will set the corresponding alphas to 0, right? So that's what masking means. So we are done with the first masked self-attention block here, which is, it's just going to use only those many entries, right? 1 to h means the number of time steps which have been decoded so far, right? Instead of using 1 to capital T1, it will only use those many entries which have already been decoded, right? So that's what you will have here. At this point, you'll have Z1, Z2, Z3. You'll also have some other things, but you don't care about them because they will not participate in the rest of the computation, right? So now going forward, you have the encoder representation coming up. So this was the masked self-attention. Now this is the masked cross-attention, right? This is the layer which is new. I need to understand what is happening in that layer, right? So let's see what happens there. Yeah. So you have this S1 to T, right? All the S representations are computed. And now again, the E's that you had, right? You had these capital T representations coming out from the encoder. You'll again pass them through your standard key and value matrices, right? And then you will have the words within the decoder or the representations coming from the decoder as the query, right? So whatever has been decoded so far, that will become the query. And then you will pass it through this normal attention network, right? So now what happens is the following, that let's understand this conceptually. So this S1 to ST so far, right? I should call it S1 to S small h, right? That is the number of words that have been decoded so far. Those have been refined representations of your original words by looking at the context also, right? The context came in through that summation alpha v, right? So these are refined representations already, but taking care only of self-attention, that means within the decoder. Now you want to refine these representations further in the light of whatever you had seen in the encoder, right? So now you want to take S1 as the input, you want to generate a Q1 from that, okay? Then using Q1 and these K1, K2 up to K capital T, where capital T was the number of tokens in the encoder, right? You will compute the corresponding alphas, right? So you'll have alpha 1 1, alpha 1 2, alpha 1 T. So these alphas tell you how much attention should you give to the ith input in the encoder while computing a refined representation for the jth decoder value, right? And now using this, you will compute your Z1 as whatever alphas you have computed, alpha 1j, into the values which are coming out of here, right? So these are going to be some vj's, and you're going to sum over j equal to 1 to t, right? The same computation happens again. You have the key, query, and value. It's just that now the attention is between the encoder, the decoder representation and the encoder representation, and you're computing a new representation for the decoder using an attention weighted sum of the encoder values, right? So that's what is happening in the masked cross attention. You are doing a cross between the encoder and the decoder, and at this level you will then perhaps get out, I don't know what I was calling it earlier, but maybe I'll just call it M1 up to T1, and then these will pass through the feed forward network to give you Z1, Z2 up to ZT1, right? So this is what the entire decoder block looks in. The new addition was this cross attention, where now the key and the value come from the encoder, and the decoder brings the query, and this masked self attention, where the only concept was of this masking, that the words which have not been decoded so far, you don't let them participate by setting the corresponding alphas to 0, right? So that's all there is to learn about the decoder for now, right? Now the last detail that we need is the output from the decoder. So you have multiple such layers within the decoder, right? And let's assume this is the last layer, which again has the same identical structure. It receives the inputs from the previous layer. It has the masked self attention, masked cross attention, then the feed forward network, and then whatever comes out, right? So suppose you get these 5 and 2 dimensional embeddings, right? And at each stage you want to predict what the next output is going to be. So you take this 5 and 2 dimensional embedding, use a matrix of size 5 and 2 cross V to give you a V dimensional output, and then you apply a softmax on that to give you the distribution over the vocabulary, and then pick the argmax from there to feed it as the input for the next time step, right? So that's what happens at the output layer, right? So we have seen the full encoder decoder. We have seen all the blocks within an encoder layer. So the encoder has many layers. Each layer is again composed of sub layers. So you have the multi-headed self attention and the feed forward neural network. The decoder again has many layers. Each layer is composed of sub layers, and you have 3 sub layers here: the self attention within the decoder, the cross attention between the encoder and the decoder, then the feed forward network. And one key property or key difference in the decoder is that when you're looking at the inputs, you only look at whatever has been decoded so far. That's why you need to do this masking, so that the inputs which are not available so far do not participate in the computation by setting the corresponding alphas to 0, right? So that's all I have to say about transformers. I'll end this lecture here, and this would probably be the last recording for the course. I will see you in the next session to clear any doubts that you might have. But we are done with the syllabus for this part of the course. Thank you, everyone.